what?
Oh, I'm sorry.
That's okay.
I actually try to normally, like in movie theaters and stuff.
Okay, why don't we get started? I am very pleased to welcome Jonathan Shewchuk from the University of California at Berkeley. Jonathan visited us back in 2002. We figured that out this morning, or he figured that out and told me. So it's been a while since he's been here, but I've known Jonathan for quite a while. I think I learned about him the same way that many people learn about him, which is through either Triangle, his famous two-dimensional triangulation program, or his equally famous paper on learning about conjugate gradient methods without agonizing pain that I very much enjoyed, and I still use pieces of that whenever I go over conjugate gradients with the class, and recommend that as a reading. Jonathan is one of the leaders in mesh generation, and he's been doing a lot of interesting work for a very long time. He's here today to give us an update on some of the work he's been doing with some of the dynamic meshing. So please join me in welcoming Jonathan Shewchuk.
Thank you very much. It's a real pleasure to be back here again. I really enjoyed my last visit, and I'm really enjoying this visit. So thanks for being a wonderful place to visit. Again, obviously I'm Jonathan, but this is joint work I'm going to be talking about with a whole bunch of smart and fun people at Berkeley. The talk is about dynamic local remeshing for elastoplastic simulation, and at some point I'll explain what those words mean. But I think the best way to start explaining what this talk is about is to show you a little video. So what you're seeing is an animation of a drip of slime dripping off of a ceiling. And you'll notice that it undergoes a pretty radical change in shape from the start of the simulation to the end. The way we modeled this was by embedding it inside a finite element mesh, which is dynamically remeshed as the domain changes shape. That's the only way to get this mesh to correctly represent this substance from the beginning to the end. Where are we? So here's your menu for tonight. We're going to start with a little bit of discussion of plastic flow and the finite element methods used to simulate it. Then, one of the main techniques that we need to use to do these simulations, again, is dynamically changing meshes. And so, before I talk about dynamic meshing, I'm going to go off on a discussion of how you take a tetrahedral mesh that may have bad quality and improve it so it has really great quality. Once we've established how to do that, I'll come back to the topic of how to use that in a simulation where a domain is undergoing radical changes in shape, or in other words, dynamic meshing. Here's a quick laundry list of the methods we're using for those of you familiar with physical simulation. And if you're not physical with physical simulation techniques, don't worry, it's not going to lose you. But we begin with the physical laws that govern elasticity, and those are expressed mathematically as partial differential equations. We use standard ones there. You generally cannot figure out the analytical solution to a partial differential equation. You have to solve it numerically, and so you have to choose a numerical method for solving it. And so we're choosing one of the most standard and straightforward methods, the finite element method. And this is a purely Lagrangian version of the finite element method. And I'll explain what Lagrangian means in a moment. Besides approximating the solution to a continuous partial differential equation, you also essentially have to approximate the geometry of the domain that you're simulating. Like, for instance, if you have this liquid simulation we did, then the way we did this simulation is by chopping it up into a bunch of very small tetrahedra. And so a tetrahedron is the simplest polyhedron you can have. It has 4 triangular faces and 4 vertices. And finally, the way that we represent physical quantities over this physical domain, quantities like position and velocity and acceleration, is by interpolating them with a piecewise linear basis functions over this tetrahedral mesh. So this is pretty much the simplest and most straightforward way to do finite elements for these kinds of complicated problems. And the talk will be mainly about the meshes, but let's talk first about what is Lagrangian finite element methods. And so what I'm showing you here is what everyone learns probably in their first finite element course if they do elasticity in that course. The way that you simulate a material is that you have two different meshes that model the same object. So on the left I have what's called the material space mesh. This is a representation of what the object looks like in its natural undeformed state. In other words, if you remove all external forces from the object and you just let it spring to its natural position, then this is that position. However, since what we're modeling is elasticity, we're taking things and we're stretching them and twisting them around, the same object will also have a world space configuration, which simply tells you how that object is shaped right now as I'm twisting it. There are two different meshes, but in a sense they're really the same mesh because topologically they're the same. They have the same edges and triangles and the same configuration. It's just that there are two different vertex positions for each of the two meshes. So there are material space coordinates for this mesh, and there are world space coordinates for this mesh. And when you have material space and world space, that defines a piecewise linear mapping from this domain to this domain. And from that piecewise linear mapping, you can calculate the strains in each element. And from the strain in each element and its material properties, you can calculate the stresses and the forces acting on each little piece of material. And once you know that, you can combine that with Newton's laws to tell you the acceleration and the motion of the material. And that is pretty much all the physics you need to know for this lecture. Yes?
All right, so finite element is it necessarily piecewise linear? I mean, the assumption is that you will not deform a triangle in non-linear ways.
There's
subdivided to make it more.
Yeah, there's certainly finite element methods that will do nonlinear basis functions, which means nonlinear deformations of the element. But for the simulations I'm going to talk about today, we just did linear and it turned out to be good enough. So here's an example of a simulation where I'll show you the animation of this later, but right now here's the idea. We take a rubber bar, we grab the ends of it tightly and we twist the top around until we've twisted it up. Then, when we're done twisting it, we let go of it and we let it spring back to its original position. And so when it ends, it has the same shape as when it started. Now if you're looking closely, one thing you might have noticed about these meshes is that the mesh in the middle is actually much finer than the one we started with. What I mean by that is that there are more tetrahedra and they are smaller. We've actually changed the mesh as we twisted the bar. Why did we do that? Because if you want to model this much twisting in the bar and you want to model it to the degree of accuracy we desired, this is not enough tetrahedra to correctly model that, at least not with linear basis functions. So we use something called adaptive refinement, which is a well-known technique for where what you do is you look at the strain gradient, the gradient of the strain within the object, and you use that as a guide for how big the tetrahedra should be. The faster the strain changes, the more tetrahedra you need to model that accurately. And we change the mesh as we go. Then when we let go of the bar, we no longer need that many elements to represent it accurately, but we care about speed, and fewer elements means more speed, so we can coarsen it back to something close to its original density. And, yes?
In this case, the two beginning and end mesh look identical. Is that a coincidence, or is this part of the approach?
Actually, that's because I don't have the figure for the after picture, so I'm cheating in here.
So in this case, we'll call it.
So no, it does not end with the same mesh. It's just I haven't had a chance to get my postdoc to make the right figure. But anyway, as I told you, there are two different spaces, material space and world space, and I just did some remeshing. Where do I do that remeshing? Well, we do the remeshing in the material space normally, and there are good reasons for that I will explain later. You could remesh in world space, and as I'll show you, that sometimes causes problems. But before we get to those problems, let me talk about what plastic flow is. So plastic flow is what happens when you take clay and you squish it with your fingers and you let go and it does not return all the way to its original position. And so there's lots of examples of substances that undergo plastic flow. When you pour ketchup out of a bottle, that ketchup is a viscous liquid, which you can also model as a plastically deforming solid. When you squeeze Play-Doh, when your car rams into another car and the metal deforms, that's plastic flow too. So there's lots of different things that undergo plastic flow, from missiles hitting tanks to goop dripping off of a ceiling. The thing about plastic flow is that you take an object, you deform it elastically, and when you let go, it does not spring back all the way to its original shape. While it was in its twisted form, it started to flow slowly towards a new equilibrium position. If you hold it twisted long enough, this might become the new equilibrium position. But in general, it flows partway to that final position and springs only partway back. Now, how do we model plastic flow? Well, plastic flow can be modeled by actually changing the shape of the tetrahedra in material space. So this is fundamentally different from how the finite element method usually works. Normally, the finite element method, you have a fixed material space mesh, and it never changes. But plastic flow means that the equilibrium state of your object is flowing into a new permanent configuration. And so you model that by changing the shapes of the elements. But here's the funny trick. After you change these elements to their new shape, it may be that they no longer fit together, or in other words, those triangles no longer form a mesh that is embeddable in three-dimensional space. How does that happen? Well, one element might stretch more than a neighboring element, so two elements that share an edge, one of them, the edge might be longer than its neighbor. Or here I have triangles around a vertex. When we started, before the plastic flow occurred, the sum of the angles around that vertex was 360 degrees. But now it's less than 360 degrees, or now it's more than 360 degrees. So you might be wondering, is that just an artificial side effect of the method we're using? And no, it's not. When you take a real-world material and you squeeze it so it undergoes plastic flow, usually after you let go, it does not return to a strain-free configuration. Rather, the equilibrium state of that material, after all the forces are removed, will still have internal strains in it. And this is actually useful sometimes, like there's special kinds of glass that are designed to have permanent internal strains that gives them special optic qualities. Intel uses microprocessors where certain fabrication layers have internal strains because that affects the electronic characteristics of the gates. And this is something you have to model well if you want to model plastic flow accurately. Yes?
So could I imagine that there's some consistency condition that needs to be imposed on that thing, and if I did, I would introduce strain back into some of those elements? Is that how I can think of it?
I'm not sure what you mean by consistency
So there's an
condition.
inconsistency here in these elements. They overlap. They
Right.
they no longer fill that volume properly. They're no longer a proper partitioning of the volume.
Yes.
But you can imagine there are perturbations of these elements that would get you back to a valid physical configuration.
Yes.
But those perturbations would introduce strain.
Yes.
And is that somehow related to this internal strain that you're describing? So
Absolutely.
some things have relaxed, and other things, in order to continue to be solid, would have to have residual strain.
That's exactly right. And I mean, obviously, when you squeeze Play-Doh and let go of it, it is still a solid three-dimensional object.
Right. It doesn't have
So
gaps, yeah.
it's just that we can no longer use material space embedding as a way of figuring out what the strain is. That's what we can't do anymore. So that's the basic problem. Now, Adam Bargtail, who is a professor right here in your department, and has done a lot of wonderful work, including the work I'm about to show you, said logically, okay, seeing as that there's no material space anymore after plastic flow occurs, let's throw away the material space. We don't need a material space. All we really need is one separate rest space for each element. So for each element, we just remember for that element what would be the equilibrium configuration of that tetrahedron if we took scissors and we cut it out of the solid so it could spring back to its natural state with no internal strain. And there's going to be a different element rest space for every element, but that's okay. As long as we have a mapping from element rest space to world space, then we know exactly how much strain is in each element at any given point in time. We just look at this mapping and that tells us. Yeah?
But then, if you have a phase shared by two tetrahedron, you're going to get different strains from each tetrahedron, right? You have a very elongated tetrahedron.
That's right.
Share space with another independent element, which happens now to be very tiny.
Absolutely.
And this makes them, everything is continued, right?
Well, that's why this object is moving. Well, that's one reason why this object is moving. So yes, you get these internal strains and they cause the object to continue to deform and change shape. Or it could reach an equilibrium state where all of the internal strains are exactly matched and then it will stop moving.
Right, and strain is first derivative of deformation, so I think strain
Yeah.
is not continuous. In other words,
strain is piecewise constant
right,
over
it's
this.
not right.
If you, because we're using linear basis functions, strain is piecewise constant. And you could use higher order basis functions if you want. So anyway, Adam and his collaborators used this idea to design a method for modeling substances undergoing highly plastic flow, which appeared in SIGGRAPH 2007. And here are some stills from an animation of a bunny that hits a bar and then slowly changes shape into something more like a pancake. So they had a lot of success with getting some really nice animations with this method. Now, they had to solve a problem during this, which is if you take a bunny mesh and you deform it until it is a pancake mesh, the mesh that was good for representing the bunny is not good for representing the pancake. So you get very badly deformed tetrahedral elements. And this is a picture from Adam's paper, and here's a substance that they are modeling that has been compressed quite a bit. And this square here is blown up and magnified here so that you can see the really skinny bad tetrahedra that appear there. Why is that a problem? Well, here's a quick tutorial on why bad tetrahedra give you bad simulations. You want to avoid elements that are too skinny, too long and thin, because they cause several types of problems. So first of all, when you have large angles close to 180 degrees, those cause large discretization errors in the finite element method, which means that the finite element method does not converge to the correct solution as the resolution increases. And the reason you have those discretization errors, it turns out, comes from the fact that you have big errors in the interpolated derivatives of the physical quantities that you are representing on the mesh. And these big errors in the derivatives aren't just a mathematical concept, though you can certainly prove things about them, but there's something you can see with your own plain eye. Right here I'm showing you two different meshes of a paraboloid, and both meshes have 200 triangles, but the mesh on the left is very good at its purpose to render that paraboloid, and the mesh on the right is very bad, exhibits this washboard effect. And the culprit in this washboard is the large angle close to 180 degrees in each one of those elements. Now, in a physical simulation where you're using a mesh like this to interpolate some physical quantity, you may not see this washboard effect, but it's there. Small angles are bad too for a different reason. They cause poor conditioning of the stiffness matrices associated with the finite element method. And everything I just said, well, I've been drawing pictures of triangles, But these things are true not just for triangles, but for tetrahedra as well. But with tetrahedra, what you need to look at are the dihedral angles that separate the triangular faces of the tetrahedron. So dihedral angles too close to 180 degrees or too close to 0 degrees will mess up your simulation. And you don't have to worry about the angles between edges, it's the dihedrals that matter. All right, so let's come back to this problem. These tetrahedra get bad. They're ruining your discretization accuracy. They are giving you ill-conditioned stiffness matrices. So what do you do about it? Well, Adam said, let's remesh. Let's recreate the whole mesh from scratch. So we throw away the old mesh, and now we have a brand new mesh of the same domain with really nice, almost equilateral tetrahedra. And then you just continue from there. And this works great. So once the bunny mesh is representing something that's no longer shaped at all like a bunny, you replace it with a pancake mesh and you're good. You can continue your simulation and know that it's reasonably accurate. So now I want to point something out. Remember earlier I talked about remeshing for a different reason, for adaptive refinement. And I told you that we remesh in material space. Well, that's not what Adam's doing because he doesn't have a material space anymore. Once you have plasticity, there's no material space. So he's remeshing in world space. So let's look at what happens with my elastic simulation of the twisty bar if I remesh in world space, like what Adam's doing in his paper. So we take the bar, we twist it up, looks good, but we need to refine, so we're remeshing it in world space. Then when we let go of the bar, it springs back to this shape. Now, again, this is supposed to be a purely elastic simulation. There is no plastic flow in this particular simulation. But something went terribly wrong. The object has undergone what's called artificial plasticity. What's happened here is that it's forgotten what its original shape is. So what causes artificial plasticity? Why is this horrible thing happening? Well, what happens when we remesh? Remember, one of the things we need to know is what is the equilibrium configuration of each tetrahedral element, which tells us through this mapping what the strain is in each tetrahedral element of our mesh. And when we take a mesh and we replace it with completely different tetrahedra, we have to resample that strain mapping so that we can figure out what the equilibrium states are for the new elements. And that resampling process inherently has error in it because these elements, you have a piecewise constant field here, but now you want to approximate with a different piecewise constant field. You can see that that's going to lose some accuracy. Yeah.
I think that this seems somewhat artificial because what I imagine would happen if I'm using Adam's technique is that you would have some. I would recommend it so that I would have some bound with the resample error. So instead of actually trying to get that particular tetrahedralization to define the configuration, I would actually probably remesh multiple times, and by doing that, I would actually, probably keep more of the accuracy. So it would not look as bad as we're showing.
So you're saying that you think that a lot of the error is because there's such a radical change between these tetrahedra and these tetrahedra?
Yes.
Okay. I actually disagree with you. I think that if you remesh more frequently, you'll have more error in the end, not less error.
Is that because the error compounds as you keep remeshing?
Yes, the error does compound with every
This is configuration because you should be able to bound the error as you remesh.
You should be able to bound the error as you remesh.
We can take this offline, but it seems to me that
Yes.
there might be a way to solve this.
Okay. I certainly would love to have a way to solve this because I don't know But it is a good and important question, but I don't have any good ideas there. All right. But anyway, given that we are incurring this resampling error, why does the bar-tail code work so well? Well, the bar-tail code is incurring some of this error, but the artificial plasticity is small compared to the real plasticity. So since this bunny is deforming so much, the additional artificial plasticity that happens, the error that is introduced on top of the real plasticity, is small by comparison, and so you don't see it. Before I go on, though, to return to the point of accuracy, let me quickly review for you the different reasons why we might want to remesh a domain. So there's roughly 3, which overlap a little bit. But again, here are reasons why we like to remesh. Number 1 being adaptive refinement when we need more accuracy, and adaptive coarsening when we need less accuracy and want more speed instead. Reason number 2 is because we can get very bad tetrahedra due to plastic flow. And if we don't fix those tetrahedra before they become almost degenerate or inverted, we're going to have a physically meaningless simulation. Reason number 3 is because sometimes domains make just radical changes in shape. So for instance, if you try to use this mesh to simulate something with this shape, just intuitively you know that's not going to work very well. And there are other examples as well where domains change shape in important ways, like fracture or cutting, if you imagine surgery simulation where you're cutting into tissue. And I want to give you just a quick example of what happens in fracture. Is here we have examples where we're smashing a ball through a plate, and we do adaptive refinement to make the plate finer as the ball goes through. Reason being that we don't know in advance how fine the plate needs to be, where the mesh needs to be fine, and once we start having cracks propagate through the plate, we need to heal the elements that were made bad quality by those fracture cuts. No, but we can talk about that offline. So anyway, let me come down to what is the goal of this talk. The goal of this talk is I want to be able to model deformation accurately over the full range of flows from purely elastic to highly plastic, large plastic flows. And in doing this, the cases that are most difficult are actually the case where you only have mild plastic flow, or the case where you have a big variation in plastic flow throughout an object, and you need the interface to be correct. Why are those the hard cases? Well, the purely elastic case is easy because you can keep a mesh in material space, so the object doesn't forget its correct shape. The heavy plastic flow case is easy because the real plastic flow is so large that the artificial plasticity is hidden. But when you only have light plastic flow, that's not true anymore. You need to do something that won't introduce as much artificial plasticity. Yeah?
So the 2 cases you said were the easy cases, the fully elastic and the fully plastic.
Yeah.
I guess the assumption is that the remeshing process itself you can do. In other words, you can do it efficiently enough or quickly enough, right? And or is that not is that sort of a solved problem, or is it something where people are still looking for something that's going faster, remeshing?
I would say that efficiency is not an issue, but I have to say this talk is about accuracy. It's not about speed at all. And everything I'm talking about is very slow. So this is all about accuracy. Let me restate that. So now that I've told you what our goal is, what the problem is we're trying to solve, I'm going to give you 2 solutions. And here's the first solution. The first solution is that we're going to bring back the material space. But it is not the same material space we had before. Before we had a material space that was strain-free, and so we could just use this mapping to figure out the strain in each element. But we know that's not possible after plastic flow occurs. But what we can do instead is we can create what we call a material rest space. And what this configuration is it is the shape that the object would spring back to if we remove all external forces and just allow it to return to its equilibrium shape. It is not a strain-free configuration. In fact, we find this configuration by minimizing the strain energy with a Newton method. Or in other words, we treat it as an elliptical finite element problem with no time component. Since this is not a strain-free configuration, we also have to use the Bardtail idea of having a mapping from an element rest space in which each element is strain-free to the material rest space. So now we actually have not 2 but 3 different spaces we have to keep track of. The element rest space, strain-free element configurations, the material rest space, which is not strain-free but is a minimizing the strain energy configuration of the entire object, and finally the world space configuration, which adds the purely elastic deformations. And if you want to know how much strain is in any one of these elements, and therefore how it moves, you have to take the composition of this affine transformation with this affine transformation. Now, what do we get out of doing this? Well, let's compare the amount of artificial plasticity that is introduced by these 2 different ways of doing things. If you do all of your remeshing in world space, then the total error you introduce, or artificial plasticity, is some small fraction of all of the elastic deformation plus all of the plastic deformation. If you use our 3-space model, and you do all of the remeshing here in this new material space, rather than in world space, then the total amount of error you introduce, first of all, is completely unrelated to the elastic component of the deformation. And second of all, it's not related to the plastic deformation in total, it's only at some fraction of the non-embeddable plastic deformation. So by using this 3-space method, you introduce much less error than if you remesh in world space. And so that's the upshot of that idea. And I'm going to spend the rest of this talk, yes?
What is
non-embeddable? Well, so you remember that these things do not fit together into a 3-dimensional object. So you compute this strain-free configuration. Now you have this mapping from, this minimal strain configuration. Now you have a mapping from strain-free to minimal strain energy. You look at how much strain is in this mapping here. And that's what this is, non-embeddable plastic deformation, the amount of strain in these yellow arrows, and which we keep as small as possible. So this is the first solution to our problem, and it makes a big, big difference. The second solution to the problem is what I'm going to spend the rest of the talk talking about. And the second solution is what's called dynamic meshing. Dynamic meshing is the idea that we do have to remesh, though now we're remeshing back in material space again. But when we remesh, we don't have to remesh from scratch. What we can do is we can just target the bad elements, try to replace them, while replacing as few other elements as possible. And so the question is, how well can we do dynamic meshing? I'm going to show you a little video that just shows you a pure application of dynamic meshing. And in this video, I've color-coded the tetrahedra according to their quality. So the very worst tetrahedra are throughout this talk. I'm going to use this color code repeatedly. The very worst tetrahedra, the ones that you really can't afford to have, will be red. And those will be tetrahedra that have a dihedral angle of less than 10 degrees or greater than 165 degrees. Then the orange tetrahedra are mediocre but tolerable. The yellow tetrahedra are so-so. The green tetrahedra are actually pretty good. The very best tetrahedra, the ones with all dihedral angles between 40 and 120 degrees, will be invisible so that you can see where the bad tetrahedra are.
This might be a stupid question since you have to work on this. Does it actually change the speed of the solver if you have a more a better composition of green? So it doesn't change the actual speed of solving if you have a better match.
Does it change the speed of the solution?
It's the accuracy.
I'm not sure if it changes the speed. I think it mainly changes the accuracy.
So this matrix would be better conditioned, wouldn't it, typically with better meshes?
Yeah, typically it is better conditioned. I think,
You
well,
might expect that in the solver would be better conditioned.
so I think in all our simulations that we do here, am I right about this? I think we're always doing, I don't even remember if we're doing explicit or implicit time stepping in this paper, so I would have to look that up. If we're doing implicit, then yes. If we're doing explicit, then probably no. If we're doing explicit, though, we still need to avoid elements that are bad because they have really short edges, because then we run into the CFL condition. So this is just a video to show you what dynamic meshing is, where we're taking a mesh that's okay and we're just twisting it until its elements become really bad. This is not a physical simulation, it's just twist the vertices and then don't let their quality fall below a certain fixed threshold. And what you see down here at lower right is a histogram of the quality of all of the elements in the mesh. And so there's the great, vast, good middle region of very good elements, or very good dihedral angles, I should say. And then on the tails, we can see color-coded the bad, the not as excellent elements. And again, the colors tell you how bad they are. We have given our dynamic mesher the task of making sure that there are no red tetrahedra. In other words, we don't allow the minimum angle to drop below 10 degrees, or the maximum angle to go above 160, well, in this case, 170 degrees. And so, as it twists, you can see at the very start of the loop, the minimum angle is about 15 degrees. And then as the dragon twists, it goes down to 10, but it doesn't go below 10, because we're using our conservative dynamic meshing algorithm to locally fix any tetrahedron whose quality drops below our threshold. So that's what dynamic meshing is. So again, one of our main goals is to change as few tetrahedra as possible, because the more tetrahedra that get replaced, the more resampling you have to do, and the more resampling error and artificial diffusion you introduce. So here I've shown what is the total cumulative volume that's been remeshed over all of the time steps that have taken place so far. So if I were to take the mesh and remesh it from scratch during one time step, that would add 100% to this number. But we can typically get away with cumulatively remeshing much less than the whole mesh, depending on how long the simulation lasts.
John, do you
Yeah.
have the number of elements that you actually have to fix?
No.
The problem with cumulative volume is that these elements are bad, so they have actually potentially very low volume.
Well, that's not really true, because to replace a really bad flat element, you always have to replace a good element next to it.
Oh, so you're counting not the number of, basically, right, you're counting the total number of volumes of things that have changed.
Yes,
So
so you can't fix a sliver without fixing some good tetrahedra next to it.
So the cumulative volume,
Yeah,
so
count
this
this.
is 20% of the volume was touched to eliminate the red text.
Yes, and if we remesh in the same place twice, we count it twice.
Okay. Oh, I see. So you can actually get over 100%.
So, yeah, these will go over 100. If you do 2 time steps and remesh from scratch on both time steps, then this is 200%. Yes. So now here's where I branch into how do we fix meshes. And so for the moment I'm going to talk about how do we take a really bad mesh and make it really good. And this is a paper I had in the International Meshing Roundtable few years ago with my ex-student Brian Klingener, now Dr. Brian Klinger. So again, our goal is to take a really bad mesh, make it really good. The methods we use are all traditional things, which I'm betting that most of you have seen. Things like bistellar flips, where, for instance, I have, well, all of these methods are methods that do local transformations, which means you take one small part of the mesh, you rip some tetrahedra out, and you replace them with some different tetrahedra that fill the same volume. For instance, what's called a 2 to 3 flip will replace these 2 tetrahedra with these 3. Its inverse, called a 3 to 2 flip, replaces 3 tetrahedra that all share a central edge with 2 tetrahedra. And now the idea is that when you're deciding whether to do one of these flips, you measure the quality of the tetrahedra before, you measure the quality of the tetrahedra after the flip, and you choose whichever of the 2 configurations maximizes the quality of the worst tetrahedron. Now, there's actually a whole bunch of bistellar flips. So, for instance, instead of, in addition to 2 to 3 and 3 to 2 flips, there are these 4 to 4 flips, where you have 4 flips that all share the same edge, and you replace them with 4 different tetrahedra that all share a different edge. And 3 to 2 flips and 4 to 4 flips actually generalize into a more general idea called edge removal, where you have one edge in the mesh that can adjoin an arbitrary number of tetrahedra, and you rip out that edge. Here that edge is called AV, and you replace them with a bunch of other tetrahedra. And the way that you do that replacement is essentially a process of combinatorial optimization. So I look at the polyhedron that is the union of the tetrahedra around this shared edge AV, and then I look at all of the other vertices of those tetrahedra, and you'll notice that those vertices form a loop around the edge AV. So this is essentially has the structure of a 2-dimensional polygon, even though it's not usually planar. It doesn't lie in a plane, but you can still use 2-dimensional triangulation algorithms to triangulate that polygon. And once you've chosen a triangulation of that polygon, then you create a bunch of new tetrahedra where for each triangle in this triangulation, there's one tetrahedron that connects it to vertex A, another tetrahedron that connects it to vertex B.
So in general, if you're triangulating a polygon, you might need to introduce a standard points. So you can show that in this case you don't. Right?
So generally when people do mesh improvement, one of their goals is not to increase the complexity of the mesh. So that's one reason, is that we don't want to make the mesh bigger than the user requests.
One of the things is when triangulating, you can have configurations of some polygons that you aren't to add standard points. To actually generate a triangulation that is not, that is, can actually be embedded in space. So in this case, it seems that you never run into that situation, right? So
into the situation where something's
of you need actually standard points to triangulate actually. Because it's a 3D polygon space, right?
Well, there are certainly cases where there is no configuration here that doesn't have an inverted tetrahedron, and you just can't do the edge removal.
Okay.
Those cases do exist.
Okay.
But, I mean, we will insert vertices when necessary, but as a last resort, and I'll talk about that in a minute. Generally, though, it's a last resort for a variety of reasons. Complexity of the mesh, cost of, it's always more expensive to figure out transformations like that. And sometimes this mesh is better than what you could get by introducing a standard point. Now, the optimization part of this is figuring out what is the correct triangulation of this polygon. And in fact, the number of triangulations of this polygon is exponential in the number of vertices around this loop. But there's a simple dynamic programming algorithm due to ClinCheck that will choose the triangulation of that polygon that maximizes the quality of the worst element in this final configuration. And in addition to edge removal, sometimes you want to do the reverse operation, which is called multi-face removal. And there's a combinatorial optimization algorithm for choosing the optimal multi-face removal operation for a given triangular face in the mesh as well. We also use numerical optimization. One of the standard techniques of mesh improvement is called smoothing. Very simple idea. You take a vertex in the mesh and you move it to a different location. And we use what's called optimization-based smoothing, where you are trying to optimize a function, like in this case, you're trying to maximize the minimum angle. And so the reason why this is the optimal location for this vertex is because these three angles here are all equal to each other, and they're the smallest angles among those triangles. And if you move this vertex in any direction, one of those angles will get smaller. So that is the optimal position for that vertex. And there are algorithms that find that position. Once you have put together a bunch of different operations for locally transforming the mesh, flips, edge removals, multi-face removals, smoothing, you can compose them into a very simple downhill climbing algorithm, which means imagine that there is a graph, probably an infinite graph, with one node for every possible triangulation of the domain you want to model, and one edge between any two nodes, such that you can get from one triangulation to the other with a single local transformation, like an edge flip or smoothing a vertex. And now suppose you assign each of these triangulations a score telling you how good it is. Now, you'd like to search through this graph and find a good mesh. You're probably not going to be able to find the optimal mesh, though. I imagine that's at least NP hard. But if you start from a particular mesh, you can do hill climbing and hopefully find a mesh that's better than you started with. And our approach in this work was not to try to figure out how to search this entire space, but rather to try to provide a set of operators that is rich enough that you just never get stuck in a bad local minimum. Before I tell you how that works, I need to tell you how we measure the quality of a mesh. We tried several different tetrahedron quality measures. One of them is, you look at the 6 dihedral angles of a tetrahedron, and you take their signs and you take the minimum of those signs. A second quality measure is you take the volume of the tetrahedron and you divide it by the average of the lengths of the 6 edges of the tetrahedron, cubed. And when I say average, I mean root mean squared. And the third one, which is very popular in the literature, is you take the radius of the inscribed sphere of the tetrahedron and you divide it by the radius of the circumscribing sphere. All of these quality measures have the property that they are 0 for a degenerate tetrahedron that has all 4 vertices coplanar, and they are maximized by an equilateral tetrahedron. And they're all considered to be reasonably good in practice for measuring tetrahedron quality. The last one, it turns out, is really numerically badly behaved as an objective function for smoothing. So I'm just putting this out there to say that I don't like this quality measure and I'm not going to discuss it again in this talk. But the first two will come back. So that's how we measure the quality of a tetrahedron. How do we measure the quality of an entire mesh? Well, it's really simple. We just write out what's called a quality vector, which is a list of all the qualities of all the tetrahedra in sorted order from worst to best. And the idea here is just that when we have 2 different meshes, say one before a transformation and one after a transformation, and we're trying to decide which one is better so that we decide whether to do that transformation or not, you compare the quality vectors of the 2 meshes lexicographically. So if both meshes have the same worst element and the same second worst element, but different third worst elements, you always take the one with the better third worst element. And this has 2 advantages. The first being that you will never get into a loop where you visit the same mesh over and over and over again. And the second being that you don't actually ever have to construct the whole quality vector of a mesh. You just have to look at the elements that you're actually changing. Our mesh improvement program begins with a bunch of old ideas taken from what I think is the best paper ever written on tetrahedral mesh improvement, this paper by Freytag and Olivier Gooch from 1997. And then we add a bunch of stuff that they didn't have. The most important new thing we add is vertex insertion. For some reason, there's always been sort of a prejudice in what's called the mesh cleanup literature against introducing new vertices at all. They always seem to feel that smoothing was okay, flips are okay, but adding new vertices is bad. And what we've found is that vertex insertion is crucial, that when you have really intractable elements that you can't get rid of any other way, vertex insertion can do the job. We also made a few other changes, like we do these operations on the boundary of the mesh and not just in the interior of the mesh, like Freytag and Olivier Gooch did, because if you have a bad surface triangulation, you're not going to be able to put a good tetrahedralization inside it. And a few other things. Once you have all these different operations, you need to put them together into a schedule that goes through the mesh and looks for opportunities to improve the elements. And that's kind of tedious, so I'm not going to tell you it, I'm just going to show you what it looks like. So in the video you're about to see, once again, the tetrahedra are color-coded by quality, with red being the really bad ones. In the lower right, we're going to have the histogram of dihedral angles, and so I wanted you to watch the squeeze in on itself as the video goes. That's annoying. There's going to be a bar on the left that shows you the minimum dihedral angle, which is presently awful, and a bar on the right that shows you the maximum dihedral angle, which is also terrible. And the algorithm tends to proceed by stages. So we're going to start by doing a passive smoothing over the whole mesh, and then we're going to look for bad elements and do other transformations like topological transformations, edge contractions, and when we get desperate, vertex insertions. So the scheduling here, the idea is generally start with the easiest and fastest transformations like smoothing, and when those are not making sufficient progress, step up to the next more expensive transformation, like topological transformations are more expensive, edge contractions a little more, and vertex insertion, for reasons I'm not going to explain, is the hardest. Now you'll notice that all of the red and orange tetrahedra are gone by now. I should explain that this video is not in real time and that this is actually a relatively slow process. So we've sped it up for you.
So how long should I run this on?
Depends how good a mesh you want. So you have your choices. You can set an angle and say, try to get this angle and stop and you're done. You can say, go on for as long as you're making progress. The reason this paper is entitled Aggressive Tetrahedral Mesh Improvement is we just wanted to see what the limit was. How far can you improve a mesh? But what we do find is that you usually get a lot of the improvement in a short amount of time. You know, the first 80% of the improvement in 20% of the time. And then it's up to you whether you want to go beyond that. Lovely. Haha. I guess I'm missing graphics lunch at Berkeley. It's just the wrong one. All right. At this point, almost all of the colored elements are gone. And one other thing, well, now they're all gone, which means the minimum dihedral angle is now over 40 degrees. The maximum dihedral angle is now under 120 in this particular example. And I want to say that when we started this research, I never would have believed that we would be able to push quality that far. I wouldn't have believed that was possible.
How long does it take this process, John?
You know, I'm going to have timings on the next few slides, but I never remember things like that, so let's go look at them. So here's an example where we've improved a tire incinerator. This is the mesh we started with. This is the mesh we ended with if we use the minimum sign as our quality measure. And this took 163 seconds on a mesh that started with about 11,000 tetrahedra. This is what happens if we use volume over length cubed as a quality measure. That took 437 seconds. I have to tell you that the timings are greatly variable because we did this with simply the policy of keep improving it until we think we're just not making progress anymore. And that can be really random. Sometimes it will run 10 times as long as another time for no reason at all. point out the comparison between the angles that we got versus the angles that Freytag and Olivier Gooch did. One of the reasons we chose this example is because Freytag and Olivier Gooch used it in their original paper, and they managed to push the minimum dihedral angle up from 0.6 degrees of a degree to 13 2/3 of a degree. They managed to push the largest angle down from about 179 degrees to about 156 degrees. We, depending on the quality measure you use, can push the minimum angle up to about 36 degrees, or the maximum angle down to about 124. So that's a big jump over what Freytag and Olivier Gooch did, and over what I thought was possible.
Where did you try to replicate the results?
Replicate?
You have all, I mean, in your framework, it seems that their optimization is a subset of yours. So there should be a set of flags that you can,
Yeah, we do have a set of flags that will use only the same operations they use, but I never actually tried it to see what angle we got.
Yeah, because it would be interesting just for reproducibility sake.
Well, the one thing I can guarantee is that we're not going to reproduce their angles. I mean, these things,
Hopefully they're
tiny change in the procedure, and you get a big change in the outcome. So the other thing to point out is that this is the quality measure you want to use if you care most about stiffness matrix conditioning. And this is the quality measure you choose if you care most about discretization error. I'm putting this example just up just to show that you can apply this to things with curved surfaces too, but that brings up a new issue, which is, am I allowed to change the shape of the domain? Now, when we were doing the tire incinerator, one of the things that makes it easy is that you can smooth the vertex within the flat surface or along the flat edge without changing the shape of the object. That's no longer true when you have a curved surface. And usually you don't have the spline data that this was constructed from. Usually you just are given a mesh. So we do have, we have thought about how to allow small amounts of longitudinal movement along the mesh so that we can get big improvements in how much we can improve the mesh by allowing a little bit of play in what is the shape of that domain. All in all, we had a test suite of 12 different meshes, and in all 12 of our test suite, we were able to push the minimum angle up above 35 degrees, or the maximum dihedral angle down below 125, depending on which quality measure we chose.
So you can use your technique for surface simplification. I know it could be a very wasteful thing to do, but I could get a very complicated surface to do like a really bad depth mesh on it, and run your algorithm, and it would actually give me like a reasonable surface in the end that I can try.
Sure, but I mean, when we actually do the mesh improvement of things with curved surfaces, we actually are using quadrics to decide how much we can change that shape.
Oh.
So we borrowed directly from the surface simplification literature there to do that. A few other things we can do that I'm not going to talk about how we do them is control the size of the elements. So far I've talked only about improving quality, but if you want to have small tetrahedra here and big tetrahedra here, it's just, we have an extra step that fixes the element sizes before we fix the quality. And you can even have whatever anisotropy you want. So we've been surprisingly successful in generating really anisotropic meshes, like our sinusoidal cow, which started as a mesh with completely isotropic tetrahedra, but simply by running it through the mesh improvement code with the right quality measure, an anisotropic quality measure, it just does the right thing. And so this sort of ends the talk within the talk about aggressive tetrahedral mesh improvement. And I just wanted you to know that our code is available for download. So if you have tetrahedral meshes to improve, please give it a shot and let us know what you think. Now, that sets us up for dynamic meshing, which is now pretty easy. We just have to make one small adjustment, which is we have different priorities now. When we did mesh improvement, our goal was to just absolutely maximize the quality of that mesh no matter what. Now our goal is to change as little as possible, and so that means we have to change the schedule a little bit. So first of all, instead of trying to improve every tetrahedron, we're just targeting the poor quality ones and getting rid of them. And second of all, whereas before I told you we were trying the fastest operations first and resorting to the slower ones only when we needed to, when we weren't making progress, now we try the most conservative operations first, the ones that will change the fewest elements, which means smoothing doesn't come first anymore, smoothing comes last. We also have to figure out what kinds of transformations we can do on smooth surfaces, because if you remember that drop of some ooze, as it changed shape, its boundary is changing shape, but the boundary triangles are becoming bad. We have to fix them. But fixing them means changing the shape of the domain. So again, the same problem that came up with the dragon. And I'm not going to say much about how we deal with that, except that we have to deal with it. But I do want to explain that in some of the animations we're using a fine triangular surface mesh, like this, embedded inside a coarser tetrahedral mesh. And this has some nice advantages for rendering, like the mesh that you render can be much finer than the simulation that you do. So from here, I'm just going to show you the rest of the video. So again, this is our dripping slime. That's a very fine triangular mesh, as I said, embedded inside a coarser tetrahedral mesh, which you can now see. You can watch the flips, and a little bit of smoothing, but not much. Mostly it's flips until it's necessary to do tougher things. This shows you the quality of the tetrahedron during this simulation. And what we're doing here is we're pegging it so that the quality of the tetrahedron cannot drop below 0.15. So what this little animation is to show is this is the twisting I showed you earlier. And here's the difference between what happens if you remesh in world space, as following the Bartail paper, versus what happens if you remesh in material space with our 3-space method, only with a purely elastic solid. So with our method, the bar remembers its original shape, but when you're remeshing in world space, it doesn't. Here's an example that lets you see what the material space mesh looks like during the twist. So you can watch the adaptive refinement happening here, and then the adaptive coarsening as well. Now I'll show you a highly plastic material, and now what you're seeing here is the pure plastic flow with the elastic component removed. The world space shows you both together, the plastic flow and the elasticity component together. But here you can see just the plastic flow. And this is the low plasticity case, which I told you is the hardest case, because any artificial plasticity is going to be visible now. But we can simulate this accurately. And here's a case where the top is purely elastic, the bottom undergoes large plastic flow, and things are good and correct at the interface. This is a different example. This is not a physical simulation. It's just a torture test for the dynamic mesher, where we're taking a sphere and spreading it out like a pat of butter until it's really, really thin. And so the only way to do a good job with this is to use really thin anisotropic elements. And so that's an embedded surface, but it's embedded in this simulation mesh. And because these are anisotropic tetrahedra, we can get away with using maybe 10,000, whereas we would have to use 1,000,000 if those were purely isotropic tetrahedra. Here's another example where this shows you just a purely elastic material. We're using dynamic refinements and coarsening. One thing I want to point out is at this point in the simulation, you see how this is kind of bulging between the teeth? That's the correct behavior. And the reason I want you to see that is to compare it with what happens if you don't use adaptive refinement. Here you can see the material space. You can just watch the adaptive refinement itself. and the adaptive coarsening. Here's what happens if you turn the remesher off and do no refinements at all. Now this is just wrong. It didn't bulge like it was supposed to. And here's the same thing done with plastic flow. Here we're showing you the material space so you can watch the plastic flow in isolation from the elastic component.
So, John, in your code, do you even specialize, do you have specialized operators for the 223 and 44, or you actually only use the generalized one that you explained to us?
So the 4-to-4 is done with the generalized code.
Okay.
There is some direct face swapping code for speed,
Okay.
and I don't remember the details of that because Brian wrote that
Okay.
part.
Pretty neat, very good.
Here's the plastic one. So I'm going to skip over how we'd handle curved surfaces and just tell you my conclusions. So first of all, the mesh improvement work in isolation, this achieves levels of quality that are just way higher than anything I've ever seen in the literature, any literature. Mesh improvement, mesh generation, mesh cleanup, whatever. Second of all, it is consistent enough that you can use it for dynamic meshing. And when I say consistent, if we allowed even one element to degenerate until it was perfectly flat, we'd be dead. The simulation is over. We can't allow a single mistake. So that kind of consistency was impossible until now. And finally, it helps us simulate plastic flow, especially light plastic flow, with far less artificial diffusion than previous methods. Thank you very much for your attention.
Thanks for a great talk. That was great.
Thank you.
People have questions, that's great, although we do need to get into some lunch. So one idea is that Structure is going to lead a lunch with Jonathan, and maybe other people could tag along and have lunch and talk about dynamic measurement. We'll take it from there.
So if there's anyone who has a question that isn't coming to lunch, then you can ask about now.
I'm not, we should be trying to go much, but I have a student that is finishing their junior defense completed today, and I have to look, and I have to look at the final version of her talk. I looked at it last night, but so I cannot go, but thank you for the great talk. This was great. Hope to see you again. Yeah. Very, very impressive. I really like this stuff, especially the aggressive that you're doing, because it's really cool.